Welcome back, students. We're going to continue our discussion of chemical bonding and chemical reactions. And in this chapter, we're going to talk about the chemistry of carbon and why it is so important. Let's briefly recap what we've talked about in the last couple of video lectures. We talked about the general layout of the periodic table and how we had nonmetals on the right and we had metals on the left, and how there would be a tendency of these to react with each other. We first talked about ionic bonding and how metals had a tendency to lose one or more electrons to become positively charged, and nonmetals tended to gain one or more electrons to become negatively charged. And then there was an electrostatic, or what we call Coulombic attraction, between the positively charged cation and a negatively charged anion to form what we call an ionic bond. But that's one type of bonding. A second type of bonding is what is called covalent bonding, or sharing of electrons. So instead of being a complete transfer of electron from one atom to the other, for covalent bonding, the atoms decide that it's better to share a pair of electrons between them, forming a bond. And there can be single bonds and double bonds and even triple bonds. So in this video lecture, we're going to talk about that element that is best at forming covalent bonds. It's the MVE, the most valuable element in terms of forming covalent bonds. That's carbon. And the chemistry of carbon is so important that we have an entire field, a branch of chemistry, a large branch of chemistry devoted to it called organic chemistry, the chemistry of carbon. To give you some perspective about carbon, there's a lot of carbon in the universe. It's the fourth most abundant element in the universe. Of course, hydrogen and helium are the most abundant. In terms of the Earth's crust, it's the 15th most abundant element. But when you look at living systems, life forms, such as the human body, it is the second most abundant element in living systems. 18.5% of our bodies by mass. So when we think of the chemistry of carbon in organic chemistry, we also think of the chemistry of living systems, and the field of biochemistry, which we'll have a chapter on, is very closely related to organic chemistry. Why is carbon so important? Well, again, because it is so good at forming covalent bonds. It prefers to form covalent bonds, that is to share. And it can share a pair of electrons with other elements in this upper right-hand corner of the periodic table, hydrogen and nitrogen and phosphorus and oxygen. And by forming a bond with itself, that is a carbon forming a bond to another carbon, this is a way of linking together carbon atoms to form larger molecules, what we call polymers. So a polymer forming ability of carbon. And carbon can form bonds with these other atoms, leading to a variety of organic compounds, many of which we find in biological systems. The bottom left shows the very simplest of organic compounds, something called methane, where you have carbon in the middle with 4 single bonds to hydrogen atoms. Each of these single bonds, which we represent as a dash, actually is 2 electrons, one of which comes from the carbon and the other comes from the hydrogen atom. So the simple way we represent one of these covalent bonds is just by a dash, and when we see a dash, we understand it to mean 2 electrons that are shared. So this is the simplest organic molecule, but you can build up a lot more complicated organic molecules. I show a couple in this slide. The top one to the right is actually an amino acid that is a component of our bodies called serine. And you can see a number of carbons linked together, but the carbons can also be linked to nitrogens and can be linked to oxygens. So a variety of different what we call functional groups can be formed. The molecule to the bottom right is another molecule in which carbon atoms are linked together. Now, every time we have like a kink with no atom drawn, that's just a shorthand way of indicating that there's a carbon at that vertex. The molecule to the bottom right is actually glucose. This ability of carbon to string together by forming bonds to other carbons or oxygens or nitrogens or other atoms, hydrogens and other atoms, kind of reminds me of Tinker Toys. I don't know if you played with Tinker Toys. Now we're into Legos much more. when I grew up, it was Tinker Toys, and the Tinker Toys kind of remind me of organic molecules, the way you can string things together. I'm just going to show you in this slide a couple of organic molecules. The first one is called benzene. Benzene, you may have heard of it. It's an organic solvent. Has 6 carbons that are strung together in a ring. If you look at the upper left, you see this ring made of 6 carbons strung together, and each carbon, besides being bonded to 2 other carbons, is bonded to a hydrogen atom. And there are what we call alternating double and single bonds, which we won't go into, but if you look at the second drawing, this is a shorthand drawing of benzene in which we don't draw the carbons because every time we have a vertex, we assume there's a carbon because carbon is so prevalent in these molecules. And so this is another drawing of benzene. And sometimes we don't even draw the hydrogens because we assume they're there, and that would be the third drawing. And the fourth drawing is what is called a space-filling model or space-filling representation of benzene. The drawing to the bottom is sometimes called superbenzene. It's a molecule called coronene, which you can see again these 6-membered rings sort of linked together to forming a larger structure. Again, the carbon atoms are oftentimes not drawn because they're understood, and likewise the hydrogen atoms are usually not drawn because they're understood to be there. And in the bottom right is a space-filling representation of coronene, and it kind of looks like a large whoopee cushion. This kind of structure of coronene can extend, and you can have even larger molecules such as this. Kind of reminds you of chicken wire. So these are a couple of examples of organic molecules and how carbon can form ring structures. We'll see a little later how it can form larger polymers. We will pause now to have a little quiz, and then we'll return and we'll talk about polymers. See you in a while.